I'm very happy that Jonas Inander from the Science Communication Department, he's here for half a year, I think, as science writer for an internship at ESO to help out with the press releases and everything. So Jonas is from Sweden, from Stockholm. He did his PhD there in 2015 in physics, or better astrophysics in cosmology, and also got 2 postdoc positions there. And even before he did his PhD, this I found very interesting. He was Antarctic driller, so ice driller, Antarctic ice driller.
Yes.
So he helped in the ice cube experiment in the South Pole. That's cool. So for this experiment. And but after doing science, he felt, so he got also for his PhD an award for the best in Stockholm, in the university, for the best PhD. Maybe he saw already his skills in writing. So he decided to be a science writer since 2019 is doing this professionally and going around and using his writing skills to bring science, astronomy, astrophysics to the public. Just writing a book now about black holes in Swedish. And maybe he tells us a little bit about this as well here. So, yeah, welcome, Jonas, and please go ahead and tell us about the black holes.
Yeah. Okay, thank you. And thanks for letting me talk here about this subject of black holes. And thanks for the great introduction. So before I start, I want to talk about not the human side of black holes, which is the topic of this talk, but the cat side of black holes, because the poster was in the cafeteria a few days ago, but then someone took it down and the poster that was left there was this one. We talk a lot in the science communication department that you can't really compete with the cat images and cat videos of the internet in terms of attention and reach. But this reminded me of a quote that I read recently by an American science journalist who said that black holes are the cat videos of astronomy. So I thought it made a lot of sense. So as we know, black holes are very popular. They're very often in the news. And for me, my journey to becoming interested really in black holes in a slightly different way, the topic I will talk about today, was this image that appeared almost exactly 4 years ago. So this is an image of the black hole at the center of the galaxy M87. So it's 55 million light years away from us. It took 55 million years for the light to travel through space and reach us on Earth. And when I saw this image, I was really awestruck. I thought it was amazing that it was possible to take this image technologically, and I will talk more about that later on. But I also felt that this kind of image has some kind of profound, deep psychological impact. It's almost like a mythological impact image with this black hole in the middle and then this ring of light around it. So I wanted to learn more about it. So I started writing a popular science book about black holes. And I did that by interviewing a lot of scientists. So Heino, Sarah and Sarah on the left were part of the team, the Event Horizon Telescope that produced this image. And then some of the Nobel laureates that have been involved in black hole research, Andrea Ghez, Rainer Weiss, and Reinhard Genzel. I also did archival studies. This is the archive of Karl Schwarzschild that you know from Karl Schwarzschild Straße 2 that we are at now. I went to telescopes up and down on mountaintops to look at the telescopes that were involved in the production of this image. That was a lot of fun. And also joined a group that discusses the historical, philosophical, and cultural aspects of black hole research. And we recently had a paper out on that. And the central theme when I started doing this was this question: what is the human side of black holes? So what could that possibly mean? So in this talk, I will tell you about one aspect of this human side of black holes that I found that I had no idea about when I started doing research. And I didn't know about it. I also written black hole articles, science articles, and I didn't know about this at all. So I'll talk about that today. And to introduce that topic, in the science communication department, we talk a lot about hooks. and leads. So if we send out a press release, you want to start with something exciting so that the journalists get drawn in, or if you make a YouTube movie, you want to start with something exciting. So I'm gonna test my hook now for this talk on you, and we'll see if it works. So the human set of black holes. So here is a black hole, same image. What could possibly be the human relationship to this black hole? And it's something that we all have in this room right now. Everyone owns one, almost everyone, and it's mobile phones. So, okay, how could it possibly be a relationship between the mobile phone that you have in your pocket and these supermassive black holes? To answer that question, we're going to go down to the Isa River and go, not physically, but imaginatively, go down to the Isa River and go all the way to the end of the Isa River. And there we will find the answer to how mobile phones are related to supermassive black holes. That was a hook. Did you like it? Are you intrigued? Please say yes. So I'm going to talk about how that works. But to do that, we need to start to answer the question, what is actually a black hole? And the starting point for that is here. It's the city of Mulhouse, very close to the French-German border. And the time is the First World War, 1915. This was a place of intense conflict. So there were battles between French and German troops over the control of this city. And towards the end of 1915, an astronomer arrives in this city to do military service. And that astronomer is Karl Schwarzschild. So this is his military identification card that I found in the archive in Göttingen, where his material is kept. So this was issued in March 1915, and you can see that at the time he was 41 years old. It says in the middle, Alter. He was also 1 meter and 69 centimeters, very important information. And if you look closely, in the middle it says Größe, so his size, his length. The 1 in the 1 meter is pre-printed. So they didn't have any military personnel that were taller than 2 meters. But then under that it says Beruf, astronom, so astronomer. So what could possibly an astronomer be doing in this front during First World War? So he was a member of an artillery unit, and he did artillery calculations to see how projectiles, when they shoot them out, how they would get affected by wind and rain and so on. And in his spare time, while doing these calculations, he also found out that black holes could exist. So how was that possible? So he writes a letter to his wife close to Christmas in 1915. I have done calculations on Einstein's gravitational theory and have worked through it. It is really something extraordinary. Here I always think that if it is right, it is as important as the entire war. So just some weeks before this, Einstein had published for the first time his theory of general relativity, which was a new revolutionary theory about how gravity works, the thing that we feel every day. And Karl Schwarzschild got a hold of this new paper that Einstein had published and immediately set out to work out the consequences of this theory. And it's when he did that he discovered the formula for black holes. So to see what he discovered, we have to take a step back and look a little bit at gravity first. What is gravity? How does it work? So if we start with Isaac Newton, this is a famous image of him. It's painted by William Blake towards the end of the 18th century. And it's actually painted as a critique. William Blake was this kind of romantic painter, and he thought that Newton, he was only obsessed with this kind of mechanical, geometrical calculations, and he didn't pay attention to the beautiful rocks behind him. And it's very funny because this is part of how we kind of construct a gendered construction of a male scientist that's shifted a lot, and Newton has been this kind of projection character for how we conceive of what a male scientist should do. And this painting is part of this tradition. But that's a topic for another talk. So anyways, Newton, he really wanted to know what gravity is. So gravity is something that we feel every day. It's something that we really can't escape from. And it's something that we might take for granted also because we experience this all the time. So, but it's important to understand it because it governs our lives on Earth, it governs the solar system, what happens in it, the galaxy, and the entire universe. So it's really important to figure out how gravity, what it actually is and how it works. And Newton's starting point was that gravity is a force. And a force is something we experience. If I want to lift an object, I have to use a muscular force to pick it up from the ground. So if I lift this one from the ground, it's all the muscles in my body is fighting from the entire gravitational pull of the entire Earth. And I win against it. So it's important then to understand, so what kind of force, what determines how strong this force is? And Newton, he discovered a formula that says that if you increase the mass of something, the force increases. So if I would increase the mass of the Earth, the gravitational pull that it exerts on me would increase. And Newton also said that if you decrease the distance to an object, the force will increase. So if we take the sun, for example, if the closer we get to the sun, the stronger the gravitational force of the sun would be. So this was kind of like a quantitative description that Newton came up with, and it worked very, very well to describe how the planets move in the solar system, how the moon moves around the sun or the Earth, how the tides work on the Earth, but he couldn't really explain why it was like this. So he wrote that I have not been able to discover the cause of those properties of gravity. So he couldn't really explain why it was like this. And we'll get back to that, but first let's take a look at this. So why do the planets move in circles around the sun, or ellipses? So Newton had this argument that suppose we place a cannon on the Earth and we shoot out a cannonball. Then it took me a long time to make this work in Keynote. I'm so proud. Then the ball will go a little bit and then fall back towards the ground. Right, everyone agrees on this. So let's shoot it out with a little bit higher velocity or higher speed. Then it will go further and eventually go back to the ground again. And if we hit the right speed, it will actually go all the way around and continue around and around and around. And that's Newton's explanation for why, for example, the moon moves around the Earth, is that it's constantly falling towards the Earth. Just like if I drop an object, it will fall towards the ground. But it's also constantly missing the Earth because the Earth is round. So it's going around on an orbit. So an orbit is a form of falling. But if we increase the velocity even more, we can make this cannonball go out into space and leave the gravitational influence of the Earth. So it will just continue out towards space. And the question is, how high velocity do you need to do that? You need to reach a velocity of 40,300 kilometers per hour. And that's known as the escape velocity. So it's very important if you want to build rockets and go to the moon and so on. This number is extremely important. But we saw that there's an interplay between how massive a body is, a planet or a star, how big it is, and how strong the gravitational force is. So different moons and planets and stars will have different escape velocities. For example, if you go to the moon, we know that the Apollo mission, they landed on the moon and they had to go away from the moon to come back to Earth. So they also had to take the escape velocity of the moon into account. And that's 8,640 kilometers per hour. So this you can calculate with the help of Newton's formula. But if you take the star, this is not the scale, then it's 2.2 million kilometers per hour. So it's much higher because a star has a much higher gravitational force because of its mass. So 200 years ago, people wondered, but if you have an escape velocity, maybe you can. We know the speed of light is roughly 1 billion kilometers per hour. Is it possible for something in space to have such a high gravitational force, a strong gravitational force, so that the escape velocity is as big as the speed of light? This is a question people asked 200 years ago. And they found out that if you take the sun and you keep its chemical composition, its density constant, but increase its radius by a factor of 500, then it will turn black. And they call this a dark star. So this was the first idea that there could be objects out there in space that had such a strong gravitational force so you couldn't see them. Light wouldn't be able to escape them. And this was really a profound shift in our understanding of gravity, because it meant that gravity was not only about dropping things to the ground or planets going around stars and so on. Gravity became related to knowledge. Because if you can't see this object, if there's no information that comes out of it, if it's completely dark, you can't really know what goes on inside of it. So all of a sudden, things turned very philosophical. And this kind of object, when they did this calculation 200 years ago, the mass of such an object would be more than 100 million times larger than the sun. So you have to start to think about objects that were extremely massive and extremely big that could maybe exist out into space. But then they said, but probably not. So they abandoned this idea. They thought that this was a bit too extreme. And maybe light doesn't work in the way people understood it 200 years ago, so they were skeptical to this idea. But the idea was there. It was the first hint of this. But then if we go back to Newton, a few slides ago, he said that I have not been able to discover the cause of those properties of gravity. So it was just the first idea. Maybe gravity works in a more weird way when it becomes very, very strong. So we have to go to the next step, which is Einstein's understanding of gravity. Because Newton had said that he didn't really understand what gravity was. He could just give an effective description of its consequences. But then Einstein came along and said, like, no, look, gravity is actually deeply connected to something else that we think about all the time, that we are obsessing about, that we're constantly monitoring, and that's governing our lives from the day we are born until the day we die. And that thing is time. So what Einstein said was the following, and when I learned this as a student, I was shocked that this is the true explanation for why things fall towards the ground, why they fall down. And I'm still shocked about it. I think it's so weird. So Einstein's explanation is this for gravity. Take a table, a nice IKEA table, and you place a clock on top of it, and you place a clock on the ground. So the clock on the ground is closer to the Earth. So if I place a clock here, it's higher up compared to the ground. So the gravitational force would be a little bit less here. So what Einstein said was that what actually happens is that the clock on the ground, it will tick slower compared to the clock on the table. It's a very, very tiny effect, but that's the reason why things fall down. They want to be where time runs the most slow. And the Nobel laureate Kip Thorne, he wrote about this in a very nice expression: everything likes to live where it will age the most slowly, and gravity pulls it there. So this is the true reason things are falling down on Earth. Because time can change. It doesn't flow at the same rate everywhere in the universe. It flows more slowly, close to mass, where you have some mass around, like the Earth or the Sun. And this can also be measured. NIST is the National Institute of Standards and Technology. They did a clock experiment with high-precision atomic clocks, 2010, demonstrates that your head is older than your feet. I always have to think like head older, slower, is it right now? So it can be proven experimentally. You have atomic precision clocks that can measure this effect. It's also important when I have the GPS system, for example. You have to take this effect that time goes faster up where the satellites are compared to the ground. And this is going back to Schwarzschild. this is what Schwarzschild discovered then that's related to black holes close to the front of the German-French front during First World War. Because Einstein had said that time can change because of gravity. He also said that space can change because of gravity. We learned about this Pythagoras theorem in school, that the angles of a triangle are always 180 degrees when you take the sum of the angles in a triangle. And that doesn't have to hold because of gravity. So we have this concept of space and time curvature. That's the essence of Einstein's theory of general relativity. And so Schwarzschild found this formula, 1915, which is the formula for black holes. He wrote it in a letter. This is the letter that he sent to Einstein and said, I found this formula. He didn't quite understand the consequences of this formula immediately. Neither did Einstein. And it actually took a long time to work out that this formula predicts the existence of black holes. And people were in doubt if it really did this. Because it's not like the sun. We observe the sun first, and then we make a model of why the sun burns and so on. In the case of black holes, the model, the formula, the mathematics appeared first. And then people have to ask, is this really something that goes on in nature? Is it something we can measure? Or maybe it's just a piece of dreamy mathematics that doesn't exist in nature. So what does this formula actually say? It says the following. Take the Earth again. And then squeeze the Earth together into the size of a Mozartkugel. So this is a calculation Schwarzschild did. He said something the size of 2 centimeters roughly. And when I go to Rewe in Garching and shop food, they always have this Mozartkugel like the exits, and I always get food and buy them. So that's why I choose this example. So if you manage to squeeze the Earth together into this size, the gravity here will become much, much stronger, because right now we feel the gravity from the mass below our feet. We also feel the gravity from all the mass that is on the opposite side of the Earth, but it's much, much further away. But if we squeeze all of that together, all of that mass will contribute much more to the gravitational strength around this object. So if you have an object this small, it will turn into a black hole, meaning light can't escape it. It's similar to that experience before of the dark stars that light can't escape. But there's also much more weird things going on here in Einstein's understanding of what a black hole is. Because you will have a surface surrounding this black hole, which is called the event horizon. Because if nothing can escape the black hole, that means that no events on the inside of the black hole can have a causal influence on events on the outside. So there's nothing you could do if you're inside a black hole that will affect anything on the outside, because you can't send any information out. You can only send stuff into it. That's why it's called a horizon of events. We can never know what happens on the inside. But the thing that's also weird with this is that Einstein taught us that gravity is about the curvature and changing properties of space and time. So that means a black hole is actually created out of space and time. In a sense, it's created out of emptiness and just a weird twisting of space and time. And what that means is that if you place one of these clocks near the event horizon and you place another clock further away, these two clocks will also tick at a different rate, just as if you place a clock here and on the ground. But here the effect can be really extreme. The closer you place this clock to the event horizon, the more the difference will be in how fast these clocks tick. And at the event horizon, the difference will be infinitely large. What that means is that if you go near a black hole and you don't go into it, but you go near it, and you stay there for a couple of hours, and then you come back to Earth, the time on Earth could have evolved by millions of years, depending on how close you got to the black hole. And it also means that if you're on the outside of a black hole and looks at something that falls into it, you will never see it actually pass the event horizon and fall into it. You will only see it kind of freezing to a standstill close to the event horizon, and with the light coming from there being less and less energetic. So there's a lot to wrap the head around about how black holes work. So instead of this schematic image, let's look at a real journey into a black hole and see what we actually would see if we fell into one. So this is a video made by Alain Riachuelo. He's an astrophysicist from Paris. He wanted to see what would you experience if you fell into a black hole, taking into account how our eyes work, and also the fact that if you move at very, very high velocities, because of the relativity of time and space that Einstein formulated how it works, light will behave in very weird ways. So there will be a lot of optical effects that's not related to the black hole itself, but just to the fact that you will be moving with very high velocities. So he took all of this into account to see what you would experience if you fall into a black hole. So let's do it. The first thing you would see is how the light of the stars behind the black hole gets bent in very weird ways because they can travel along different paths around the black hole. And you will see how it becomes brighter and brighter because your velocity increases, which causes what's known as a Doppler effect as you fall into the black hole. There will be a green flash when you pass the event horizon. That's just a signal that now we passed the event horizon. Nothing special by itself happens there. There's no sign telling you, here's the event horizon, now you're passing the surface. You just continue into the darkness of the black hole. And will you survive the journey? That depends on the size of the black hole. Rather counterintuitively, it's better to go into a big black hole than a small one. The reason is that a big black hole, the reason is that the effect that you will experience when you fall into a black hole is something called tidal forces. If you fall feet first, your feet will at some point start to fall faster than your head, and you will start to get stretched out. You will not get stretched out in a way like if you have like a torture rack that's stretching you in the medieval ages. You will get stretched out on all levels of your body. So your nerves, your skeleton, your muscles, your cells, your atoms, subatomic particles, everything will get stretched out. And there's no way you can experience that on Earth. You need the extremely strong gravity that you have in a black hole. But this effect is less for a big black hole. Just in the same way you can imagine when we stand on the surface of the Earth, it looks kind of flat. You don't really see the curvature of the Earth. But if you stand on the moon, you see the curvature of the moon more clearly, and it's smaller. So in the same way, a big black hole, the space-time curvature is actually not as extreme close to the event horizon compared to a small black hole. So let's make another journey and see how this works. And this time, we're doing the same journey, but we also want to see what goes on around us, what do we actually see behind us and so on. And so this is a dome projection. So you have to imagine how the sides here is something that you kind of would fold over the dome inside the supernova as we go into the black hole. And this allows us to see a bit more. Notice, for example, the Milky Way and how it appears twice, also on the other side of the black hole, because of the weird way that light can travel around the black hole. Notice also how, once again, light increases around the black hole, and also the entire sky seems to get squeezed around to the borders of the black hole. It's like the sky will be falling, the sky behind you will be falling over you, and it will become darker and darker and darker almost everywhere besides this ring of light that gets focused around the black hole. Now we're actually on the inside of the black hole. What we will see is all the light of the galaxy being focused into an extremely bright ring of light that will surround us before we die. So it's a very dramatic way to die. And of course you could wonder, but what happens when you reach this final stage inside the black hole? It almost looks like you're landing on a dark surface. This is known as the singularity. It's a point of infinite gravitational force inside the black hole. And we don't really know what happens there. Nobody can go into a black hole, check out what's going on, and then go back and tell about it. The only thing we can send into a black hole is actually our mathematical equations. And they break down there. And even though there has been decades of research trying to formulate what's known as a quantum theory of gravity that could explain this final point inside the black hole, it's still uncertain actually what happens there. But this was all theory. Do these objects really exist in nature? A lot of people doubted that. They were so extreme, including Einstein, who wrote an article 1939 saying that basically that black holes cannot form in nature. It's impossible. At the same time, there were other articles written that said that it's actually possible. So there was a debate going on about that. Today, we know that if we peek straight into the Milky Way with extremely good telescopes, such as a very large telescope that ESA has built in Chile, we have to look really far, and we have to think, how could we possibly see a black hole if it's black? And the idea goes actually back 200 years to this Newtonian idea of dark stars that, okay, if something is black, that doesn't mean that you can't see it or infer its existence. All you have to do is see how things move around it. So maybe you could look at the stars that move around such a dark object, and from the motion of those stars, you could infer the existence of a black hole. And that's exactly what was done by the group by Reinhard Genzel using the Very Large Telescope in Chile and Andrea Ghez using the Keck Telescope on Hawaii. So here is the data from the gravity collaboration showing the motion of stars around some kind of object that is very, very heavy. It weighs several millions of solar masses, and it causes these stars to go around on very fast orbits around it. And they can complete an orbit in just a couple of years and decades. And in fact, we are also going around this black hole right now, but for us it takes around 230 million years to go around the galactic center. And this was awarded with the Nobel Prize, this observation, in 2020, so 3 years ago, for the discovery of a supermassive compact object at the center of our galaxy. And Roger Penrose from the UK also got a prize for his theoretical work showing that black holes could indeed form in nature. But again, a black hole is kind of black. Here we saw how the stars are moving around a supermassive black hole. But can you see the darkness directly? And you can. You need a light source. Just as if you go into a dark room and you want to find some object there, you turn on the light to find it. You can't see a dark object in a dark room. You need a light source. And it's the same for a black hole. If you have matter that goes around it, so gas, that because of its fast movement, it starts to glow intensely, you can actually start to see the darkness of the black hole in that light. So it gets imprinted on the light that gets sent out from the gas that swirls around the black hole. So the matter becomes kind of like a lamp that lights up the black hole, but it doesn't light up it in the form of light, but in the form of darkness. And that's known as the black hole shadow. And that's exactly what Event Horizon Telescope collaboration could observe also for the supermassive black hole at the center of the galaxy. So here they managed to image, also with the help of ALMA, and when we see ALMA in press releases, we always write, comma, of which ESO is a partner. So ALMA, of which ESO is a partner, helped him create this image. What we see here is the gas that's moving. We don't see the motion. It's like a frozen image of the gas that's emitting light as it swirls around the black hole. And in the future, they want to create even movies of the gas moving around the black hole. They do this by using telescopes all placed all over the Earth at different continents and combining the data of these telescopes and actually using the rotation of the Earth to map out different parts of the image of the black hole. So the Earth itself becomes part of the telescope, like a mega telescope that can image this black hole. They also managed to get an image, that was the first image I saw in the beginning, of the black hole M87 star. that lies 55 million light years away from us in another galaxy. And if you compare these two black holes, they're actually of very different size. So the other black hole image, it's of a black hole that's much, much larger than the black hole at the center of the galaxy. And if you compare it, if you first look to the right, we have Sagittarius A star. So the star is not that it's a star, it's just a terminology that's used. So the black hole and the gas that emits the light has the same size as roughly that's spanned by the orbit of Mercury in our solar system, whereas the other black hole, it's even larger than our solar system. So these are enormous black holes that exist in the universe. So what's their role? What do they actually do? Well, one thing that they do, this black hole that the image in the galaxy M87, 55 million light years away from us, the galaxy is up there to the left, and the black hole wouldn't even be a pixel in this image. So this is an image of the entire fuzzy galaxy up there, and it shoots out these enormous jets. And it turns out that this is actually what supermassive black holes do, is that they can create enormous jets in the universe. So it's not correct to say that black holes are like vacuum cleaners that suck everything in and grow as they do so. They actually also shoot a lot of material out and shoot a lot of light and energy out from them. So this is a simulation, and astrophysicists are trying to figure out exactly how that works. That black holes actually expel matter away from the galaxy. And this is what it looks like for real. So this is a galaxy. Now I always confuse two galaxies. Is it Centaur A or Hercules A? I always mix them up. So this is one of them. Very, very far away. And the galaxy is the one in the middle. And you see these enormous jets being shot out from the galaxy. These jets can carry as much energy and be as luminous as the galaxy itself, or even more than the galaxy that they are ejected from. And this was a big mystery. How could something in nature create these huge energy productions that become larger, create structures that are larger than the galaxy themselves? And people believe that it's probably because of the powerful gravity that you have around a supermassive black hole. And such a black hole, yes, it's big compared to our solar system. It's kind of same size, comparable. But compared to the galaxy, it's extremely small. It's like comparing a grain of sand with the entire Earth. It's a very, very small thing compared to the entire size of the galaxy. So something extremely small on the level of the galaxy can create structures that are even larger than the galaxy itself. It's amazing. So this was one of the big questions to figure out how that's possible. And what astronomers learned was that these black holes, they are actually there when at the center of most galaxies. They are there when the galaxies are born, when they are created. They produce at some point in the time, they can produce these enormous jets. They can also regulate the way stars are formed in the galaxy. So they actually have an influence on the evolution of galaxies. So they are part of the galactic ecosystem. And here's one of my favorite quotes about black holes. It's written by Crystalline Smith in a tweet. So she's an astrophysicist. And she says, "Stop demonizing supermassive black holes. They aren't lurking in galactic centers. That's their home. They built it. They aren't monsters. They don't ravenously consume everything they see. Keep a respectful distance and you'll be fine. They are just beautiful giants." I really like this quote because it shows that we need to change our understanding of what a supermassive black hole is and what it does. It's actually something creative. It's something that imprints a structure on the galaxy where it lives. And it's also creating some of the most powerful light in the universe that we can see all the way across the universe. So they are beautiful giants. And in the comments, as you see, this got a lot of retweets. someone compared it kind of accurately to white sharks. You know, when the Jaws movie came, everyone thought like, oh, sharks, they're so horrible creatures, monsters. But biologists knew and also said that, no, look, sharks are extremely important for the ecosystem of the ocean. They aren't monsters. And it's the same with the supermassive black hole. They play an important role in the evolution of galaxies. But let's summarize, because we don't only have supermassive black holes in the universe, we also have small black holes called stellar mass black holes. So let's first look at the supermassive black holes. So they probably exist in the center of most galaxies. So they are, and they can produce the most powerful light in the universe. So they're intricately linked to the evolution of galaxies. They can have a mass of millions to billions of suns. So imagine that, taking millions of billions of suns and squeezing that into a volume that's smaller than a solar system. And their origin is actually unknown. That's one of the great astrophysical mysteries today, how these supermassive black holes are formed, what's their seed, and how can they grow so massive, and it turns out very, very quickly in the lifetime of the universe. But then we have stellar mass black holes. In the Milky Way, astronomers believe there are hundreds of millions of them that exist only in the Milky Way. So they are also common. They are not born when galaxies are born. They are instead born when certain massive stars die. And they can have a mass of a few to tens of suns. So they are related to the death of stars and not the birth of galaxies. And the closest one that is known is 1,600 light years away from Earth. So that's about a factor of 400 compared to the closest star to the sun. So they're pretty close, and probably we will see even more black holes that are even closer than this in the future. But, okay, now you say, okay, this is very fun, great, but what about the hook? What about the mobile phone? This was what I was going to talk about. So, yes, and I'm going to finish now with this story of how these supermassive black holes actually are related to our mobile phones. And it's all about navigation. So I guess most of you have used Google Maps or some similar navigation app. You know, you want to get from one point to another point. So imagine that you lived a few hundred years ago and you wanted to do the same thing. You want to get from one point to another point, from one part of the ocean to another part of the ocean, or from one part of the desert to another part of the desert. What you would use is the stars. That's how you would navigate back in the days, i.e. most part of history of humanity. So why do you use the stars? Well, the point is that if you want to see how your position from one point to another point changes, you need to compare it with something that doesn't change. You need some kind of point in the sky that's fixed, that doesn't move, and you can use that as a reference point when you navigate. The problem today is that the stars, they are moving too. So they are not fixed in the sky. And we can measure the movement of the stars to extremely high accuracy with the Gaia satellite, for example. And today, the precision that's needed in terms of studying how positions change on the Earth is on the order of millimeters. For example, when they wanted to take the image of the black hole at the center of our galaxy, they need to know the position of the telescopes to millimeter and centimeter accuracy in order to be able to combine the data from all the telescopes in the right way. So we need to know we need to know the position extremely well. That means that we need to find points in the sky that are extremely fixed, that are not moving. That in turn means that we have to look as far away in the universe to see these points that are fixed. They don't move because they're so, according to us, they don't move because they're so far away. That means that we need to find something that can emit a lot of light all the way across the universe so that we can see it on Earth. And that something is exactly what we just talked about. Supermassive black holes create the most intense light phenomena in the universe. So when we look up into the sky, we see the stars. We can map out how they are moving. In order to find fixed points in the sky, we need to look even beyond the stars to other points in the sky. And that's exactly what astronomers can do. They can look at something called quasars, so extremely far away, bright points in the sky that are created by supermassive black holes emitting these enormous jets that we can see all the way across the universe. So that means that supermassive black holes, they can actually create the phenomena that we can use to calibrate how we measure positions on the Earth, thanks to their intense gravity. How do you do that in practice? You go to Munich, and you go down the Isar River, so it's this central road 92, all the way to Deggendorf. So that's where Isar ends. And you go a little bit up, and you will find the Geodätische Observatorium Wetzel. Looks like this. So this is a radio telescope. And it measures quasars. So it measures these points on the sky. And it does that together with a whole network of telescopes distributed all around the globe, called the International Very Large Baseline Interferometric Network. So all of these telescopes, we also have one in Sweden in Onsala. All of these telescopes take all their data, crunch that data into computers, and out of that, they get a map of the sky of these different quasars. And this sky map is called the International Celestial Reference Frame. So it's our best and accurate reference frame in the sky of points in the sky that are fixed, that we can use to compare points on the surface of the Earth, how they are changing relative to these points. So ECRF3, it says up there. So this is a sky map. These are the different points, and the yellow ones are the ones that they actually use in practice for this system. And they're always updating this catalog of this reference frame, this sky map. So what they can do with this, for example, is to measure continental drift. They can see how the telescopes themselves that are looking at these quasars, how the telescope's position is changing relative to these points in the sky. So if you look at the legend down here, you have a red arrow that says VLBI. That's that measurement. That's also down there at the end of the Isar River at the Geodetic Observatory. And you can see things such as that Europe is moving away from America, whatever consequences you want to draw from that, the conclusions. And you also have other systems such as GPS, which we know from our navigation app. The GPS system is something we use all the time. SLR and DORIS are other ways, other satellite types of measurements that they also use to measure the Earth. So there's an entire system that scientists use today to measure how the surface of the Earth is changing, such as with continental drift, how the ocean change, the uplift of the continents, the rotation of the Earth. So they use all of these systems to get a very accurate understanding of the Earth. And up there you have quasars that they actually use to calibrate the system. So the answer to how you use your mobile phone is that when you use Google Apps, you're actually using a system that is partially calibrated with the help of quasars that are created by supermassive black holes. So that's one example of the human element of black holes and how we can use them that I had no idea about when I started doing research about black holes. So to summarize, black holes are, I would say black holes are paradoxical because they are massive. They contain a lot of mass, all of the mass that created them. But at the same time, they created out of space and time. In a sense, they're empty. And at the same time, they can contain a lot of mass. There's a duality going on here between something being very massive and at the same time being very empty. They are present at the birth of galaxies and the death of stars. So another one of these dualities. They are also very creative and destructive at the same time. They are behind the most intense darkness and light in the universe. So another duality. They are both the darkest and creating the lightest phenomena in the universe. And they are also a tool that we can use to navigate and understand the surface of the Earth. So they are space-time objects that we use to better understand how the space of the Earth changes with time. It's quite amazing how we as humans have managed to actually incorporate black holes as a part of our technology. So my final slide to conclude is ESO's role. So if you go to the press archive of ESO, and up on the right, you type black hole to see what has ESO done with this. You will find 202 items in the press archive. And it's quite funny because the earliest one goes back all the way to 1986 and concerns the construction of the Very Large Telescope. And if you read that, it's a very interesting sentence that says, the VLT will achieve angular resolution, the technical stuff, in order to search, look at the galaxy nuclei, which may have black holes near the centers. So they didn't know in the 80s, is there a black hole there or not? People thought, yeah, maybe it's something else. We have to build a telescope and find it out. And ESO did it and showed that indeed there is a supermassive black hole at the center of the galaxy. So I think that's really cool. I think everyone at ESO has contributed to this. So it's not only scientists and engineers. I think everyone, people working in the reception, cleaners, IT department, interns, like everyone contributes to this great science and spreading that science. So I think everyone at ESO should be very proud of themselves for contributing to this. So that's the end of my talk. So if you want to follow the last steps of my neurotic journey, this is it. Yeah, thank you.